Okay, this will be the lecture for Chapter 17, Electric Potential, also known as voltage. We'll be introducing several new key concepts. First, that we can have potential energy due to electric fields, and that will lead us into a discussion of voltage or potential difference. Turns out that this potential is related to the electric field, so we'll go ahead and do that. Introduce a new unit of energy, the electron volt, and talk about the potential due to many point charges. And then we'll kind of finish off by talking about capacitors, dielectrics, and how capacitors can store energy. Now let's just think kind of conceptually for a second. If we had a positive charge held in between two plates, what would happen to it? Well, we know that the electric field is kind of going to be pointing away from the positive and towards the negative, and this positive charge right here is going to feel a force that's equal to the charge times the electric field. So that's going to be the force that it feels. You can also kind of think of it as trying to flee away from these positive charges, and it wants to go towards these negative charges. So if we release this guy, it's going to essentially fall down. This is kind of analogous to if we were to lift a ball up off the ground. We're giving it some potential energy, and it's going to fall to a region of low potential energy. So what we can kind of do is we say over here, this charge has some high potential. Over here, it's got some low potential. Now, what is the change in energy? Well, it's going to be essentially how much work is lost. Remember that work is going to be equal to the force multiplied by the distance, and so it's going to be equal to the charge multiplied by the electric field multiplied by the distance, and it's essentially the negative work, so it's how much work was lost. So the potential energy difference between these two plates is going to be equal to negative charge times electric field multiplied by the distance between them. Now, the next thing that we're going to define is electric potential. It's just a little bit different than electric potential energy. Be very careful. It can be kind of sneaky whether we're talking about electric potential energy or electric potential. Essentially, it's defined as the potential energy per unit charge. So kind of looking at this charge right there sitting in this sitting in that electric field, we're going to say, hey, we know that it has some potential energy, but let me just kind of take this charge away for a second. Still, I know that if I put a charge there, it's going to have some potential energy associated with it. This is kind of very similar to when I define the electric field as taking the force and pulling out the charge. So this potential is going to be just the potential energy divided by the charge. So what it says is, suppose I know what the potential is and I stick some charge in there, I'm going to know how much energy it will have. The unit for electric potential is something you're fairly familiar with. It's going to be the volt, and it's simply going to be a joule. You can see the unit for that guy is going to be joule, and divide that guy by a coulomb. So that's kind of the basic definition for the units of a volt. So kind of in other words, if I suppose I said I had something and it had 12 volts of electric potential, you're going to say, well, that means that if my charge is just going to be 1 coulomb, that means that I must have 12 joules of energy associated with it. Now it turns out that we can actually only measure the change in potential. So what that does is we're going to say we can actually measure this VBA, where here we have B and here we have A. We can only measure the potential difference. We can only measure VB minus VA. Remembering that the potential is simply the potential energy divided by the charge, really what we can kind of do is say we can define 0 to be wherever we want it to be. Typically we do that to the negative side of the house. And kind of what we're left with is just VBA is going to be equal to the work that it takes to move that charge from B to A. More or less what we're doing here is we're doing the same thing that we did with, say, a dropped ball, where here we have a ball and we're going to drop it from some height down to the ground. But really, suppose that this ground is just the classroom floor. Here we're defining there to be a potential energy equal to 0, but if we're on the second floor of a building, it could actually fall a little bit further. So I'll kind of strike through and put a 0 right there. We can take this analogy between gravitational potential energy and electric potential energy just a little bit further. Consider two rocks with different masses. Remember, gravitational potential energy was mass times gravity times height. Obviously this rock has more mass, and so it's going to have more potential energy. The same is going to be true for charges. This charge is going to have less potential energy than that charge does right there. And also the height, if we wanted to change this height, we would change the gravitational potential energy. Similarly, we would change our potential, or our voltage, that would change the potential energy that these two charges here have. Now let's come back to this definition I've already introduced, that work is just going to be charge multiplied by potential. Very typically, what we do is we're given a battery. Maybe we're going to say this is going to be just like a 12-volt battery. What's really going on here is we're going to have essentially 12 volts up on top. We're going to have, say, 0 volts down on the bottom. And what we're looking at is how much work does it take to move one single charge, say that charge right there, all the way up to the tippy top of the battery. We also know that work, kind of the classic definition, is going to be the force times the distance, and we know that the force is going to be the electric field multiplied by the distance. So you can kind of relate these two guys right here and say, hey, look, the amount of work, whether defined mechanically or whether defined electrically, is giving me kind of a very similar equation. So this tells me that I can write VBA simply going to be equal to negative electric field multiplied by distance. And lastly, we can go ahead and solve this for electric field, which is actually fairly powerful. It allows us to write the electric field if we know the voltage and we know the distance. Something else I mentioned in the last chapter was occasionally you're going to see electric field have units of volts per meter. You can kind of see in this definition right here, we're going to get those units. You can check this with your SI, do some unit conversions, and this will actually work out to be a Newton per Coulomb, but I leave that as an exercise for the student. What we can now do is we can define lines of equipotential as well as surfaces. Equipotential means essentially constant voltage, constant potential. And let's just take a quick look inside of two parallel plates here. Here we have some positive charge, some negative charge. We know that the electric field is going to go from positive to negative, and we know that the magnitude of it is actually going to be constant from the last chapter. What we can then do is say, hey, where do we have constant potential? Well, I know that the potential is going to be equal to the electric field multiplied by the distance. First, let me say, hey, I'm going to set this plate over here equal to 0 potential. Now I'm going to go some distance, and if I go the same distance here, then I know that I'm going to have some constant potential because I've simply gone the same distance. Electric field is the same. So here I might have 5 volts of potential. If I go twice as far as the 5-volt line, I'm going to now have a voltage is going to be equal to electric field multiplied by distance. Now I'll have my 10-volt equipotential, then 15, and then 20. Turns out that these lines of equipotential are going to be perpendicular to the lines of electric field, or you can say it vice versa. Electric fields are going to be perpendicular to lines of equipotential. And also that the surface of any conductor must be at an equipotential. What that means is if I put some charge, have some voltage anywhere on this plate, it's going to spread all out, and the potential down here must be equal to the potential up there, because this, by its very nature, is a conductor. Now we've already taken a look at the electric field lines for just an electric dipole, two opposite charges, so they're kind of shown in red, which is what I've already kind of shown you. Let's take a look at equipotential lines, or lines of constant voltage. Suppose we'd say that here we have 0 volts, and over here we have, say, 20 volts. These equipotential lines must be perpendicular to the electric field lines. So we'll pick the simplest possible case right in the middle. Kind of see how that green dashed line is perpendicular. And then over here, all of the green dashed lines are going to be perpendicular to the electric field lines where they touch it. And kind of the same over here. So you get kind of this interesting looking shape. Now, symmetry says if this is at 0 volt and this is at 20 volts, this line here is going to be halfway in between. So that would kind of be our 10-volt line of constant potential. Maybe this would be our 7.5 volt line of constant potential, and so on and so forth. So along these green dashed lines, the potential, the voltage, must be the same. Now, one concept of energy that we need to talk about, it's kind of introduced here in 17.4, but it's not going to really bite us until chapter 27, the very last chapter, and that's this unit of energy called the electron volt. Essentially, we've been talking about joules of energy, and that's great for talking about mechanical objects and so on and such forth. But once we're talking about things on the atomic scale, it's actually going to be talking about really small energies, and that's where the electron volt has its strength. Essentially, if you remember that the potential is going to be equal to the change in potential energy divided by the charge, 1 electron volt is going to be the energy gained by one single electron moving through a potential difference of 1 volt. So we have 1 volt is equal to the change in potential energy of a single electron. Electron has a charge of 1.6 times 10 to the negative 19th. So we're talking about some potential energy that's going to be equal to 1.6 times 10 to the negative 19th joules, and we're calling that one single electron volt. So a really small amount of energy. Now we can also talk about the electric potential. Again, we're talking about voltage due to just a single point charge. The derivation actually is using calculus, and I don't think you really want to see that. So I'll simply give you the result and let you chew on it from there. So we can write the potential, the voltage, of a single point charge with charge capital Q is going to be equal to that K that I've already talked about, and multiplied by the charge, multiplied by the radius away from it. One thing to note, that this is not going to be squared, which in the case of electric field it was squared. If I were to say, hey, here I've got a point charge that's going to be positive, I've got my lines of electric field in blue, then again my lines of constant potential, constant voltage are going to be perpendicular to that, so it's actually going to be kind of going out in circles. Where if my radius was 0, I would have potentially infinite potential, and it's going to get smaller and smaller and smaller and smaller as I move further away from my point charge. I can also write this in the language of the permeability of free space. Suppose we wanted to plot the potential as a function of radius. Well, we know the potential is just going to be kq divided by r, and as I said in the last slide, if r is 0, we're going to have kind of infinite voltage. This guy kind of asymptotes up like that, and it's going to die off simply like 1 over r. If the charge is negative, so put a negative sign right there, it's going to be the same thing, only it's going to be flipped over on the negative axis. It's going to have a essentially negative infinity way out here, and then the potential becomes less negative and less negative and less negative, and actually as r approaches infinity, we would say the potential is going to be equal to 0. Now, one nice thing about electric potential compared to electric field is that potential is actually going to be a scalar quantity. Electric field is going to be a vector quantity. So we care about direction for electric field, we don't care about it for potential. So if I wanted to say, hey, what is the potential here at point P? Well, simply say, okay, well, here I've got 2 charges, and I'll say this is R1 and R2. The voltage at P is simply going to be equal to the potential at 1 plus the potential at 2, which is going to be equal to kq1 divided by R1 plus kq2 divided by R2. Again, note that there is no squared right here. I just simply add them together because they're just numbers. If I was talking about electric field, I'd have to worry about direction. I'd have to say, okay, well, this is going to be the electric field from 1, it's going to be electric field from 2, and now I need to break that into x and y components and kind of vectorially add that together, and depending on the relative strengths, maybe it would be here, maybe it would be there, or maybe it would be over there. So electric field, I have to worry about the vector component. Potential, I do not.